Okay. Okay. Yeah. Well, thank you very much, Duncan. So as Duncan said, I'm Stuart Harper. I'm a postdoc at the University of Manchester, and yeah, I'm going to be talking about the CBAS survey, or the C-band all sky survey. So, it's just yeah, okay. So this is a picture of the collaboration as it stands at the moment. We're currently collaborating between University of Manchester, University of Oxford in the UK, and Caltech in the US. We also have a number of other collaborators who work in South Africa and the IAC as well, Mike Peel from the IAC, who will be talking after this, I believe. So before I talk about CBAS, I just want to give maybe just a small preamble of motivation for why CBAS exists. So this is a woefully incomplete list of low frequency surveys, but probably more of the more important ones for CMB science. And what you can see in this table, the first one should be well known to everyone, the Haslam 1982 408 megahertz survey, which was this combination of Jodrell Bank and the Parkes telescopes to do an all sky survey in intensity. Now, this map has been the go-to for CMB science for tracing low frequency programs such as synchrotron emission for decades. WMAP, Planck, and even still beyond Planck is still using this map, as we saw yesterday. And that's just because it's the best one we have, and it's the best tracer at very high signal to noise, but it is known to have numerous issues, such as not knowing not complete information on the beam, systematics such as noise, properties across the map, and the calibration of the map as well. And also a key problem with it as well is that it doesn't have polarization, which is very important, of course, for B mode science. So in recent years, we have had polarization low frequency surveys start appearing, such as SPAS, which is the most recent one and probably the best one available at the moment, just in the southern sky, which is available in polarization as well. But we also have these 1.4 gigahertz surveys by Wollerburn and Testori in 2006 and 2008. However, these maps still are known to have systematics that are problematic for the CMB science. And for example, you can there is actually a recent paper that came out by Wayland et al., part of the old WMAP team, just a few weeks ago, who actually go through some of these problems related to when they were trying to measure the polarized spectral index of the synchrotron emission across the sky. So what we want to do with CBAS is basically produce a premier, basically the best low frequency survey that we can that will be most useful for CMB science going forwards. So with that in mind, let me tell you what CBAS is. So CBAS is a 5 gigahertz all sky survey where we have 2 telescopes. We have one telescope in the north, set in the Owens Valley Radio Observatory in California. This northern survey has actually already been completed, and we are in the sort of final stages of data quality checks, essentially, for mostly just in the polarization side of the data. The actual sensitivity of the maps is very, very low. We've got it's very low. The sensitivity of the maps is very high. The noise levels are very, very low, where we have 0.1 milli-K RMS per 1 degree beam, which translates to about 0.0125 micro K per 1 degree beam at 100 gigahertz, which, for context, is several times lower than the typical fluctuation scales of the synchrotron emission at those frequencies. So we have high signal to noise across most of the map, usually signal to noise of 5 or better for 90% of the map, and I'll show that a little bit later. We also have a southern part of the survey, which is currently ongoing, but has unfortunately been delayed, mostly due to COVID-related issues. meaning that engineering staff haven't been able to maintain the telescope over the last couple of years. But that telescope is actually set on the square kilometre array site in the Kourou in South Africa. But we do plan to start getting that together over the next few months and continuing that survey. So what makes CBAS special is that we have, it's been designed from the ground up basically to be the best calibrated and lowest noise low frequency survey that we can design. So this is with that in mind, this is the optics that we have for the Northern Telescope, which the two key features of this are the secondary dish is actually supported by a microwave transparent foam. That means that we do not have to have any struts supporting it. And this is key because that means that we are able to get a circularly symmetric beam pattern on the sky, which is much easier to deconvolve and much easier to control when it comes to removing this feature from the actual final maps. On top of that, we also have a radio absorbing baffle, which means we have very good suppression of the far outside lobe. So the vast majority of the power of the beam is actually forward facing. It is only within the first couple of side lobes and the main beam, which is much easier to control. In terms of the receiver, we, for polarization, we are a correlation receiver. So we correlate the right and left circular polarized feeds inputs together to get instantaneous measurements of the Q and U Stokes parameters in the horizon reference frame of the telescope. And we have a continuous comparison radiometer where we are comparing the right and left circular polarized inputs with a known reference load to get intensity. And together, these two methods actually allow us to have very good control on our correlated noise. And in fact, I won't really be talking much about correlated noise in this talk, just because the correlated noise is so low that it's not really a major issue within the survey. So this is the maps as they stand at the moment. On the left, we have the intensity map, and on the right, we have the polarized intensity map. These two maps are on linear scales, and you can see immediately the fidelity and signal to noise that we have across the whole sky. In intensity, the signal to noise is very high at all points. We actually are measuring diffuse emission across the entire sky, even in the lowest emission areas over here in the sort of top right area of the plane. But yes, you can clearly see the North Polar Spur, the Galactic Plane, Barnard's Loop down in the Orion region. You know, the fidelity is very, very high. And if we look at the polarized intensity map, we can see very similar structures. We can see that we are detecting the North Polar Spur, many of the synchrotron loops that are well known from the WMAP and Planck analyses earlier on, or not earlier, in the past. And we are actually detecting the whole sky to signal to noise ratios, well, 90% of the sky to signal to noise ratios of 5 or better. The other key thing actually about the CBAS survey as well is that if we look at the galactic plane here, you can actually see that the signal, the polarized signal is quite scrambled. That's because of Faraday rotation. But unlike other low frequency surveys, including SPAS and the other surveys I mentioned earlier, the area of the sky that is actually impacted by significant Faraday rotation is pretty much just relegated to just a few degrees around in galactic latitude around the galactic plane. So we are very easily able to translate this emission to higher frequencies, such as WMAP. Now, what I want to talk about for the rest of this talk is just some of the challenges that we had in terms of producing these maps, and also some of the quality and fidelity checks that we did to verify that this emission is that these maps are the best that they can be. So one of the major issues with a ground-based experiment is that your telescope is sitting on top of a 300K load that basically fills half of the hemisphere of the sky above you, right? So you've got the sky above you, but you've got the ground below you. And even though we have very good control of our far outside lobes, that emission is still integrated extremely bright relative to the sky. So what you're seeing here on the screen is, on the right, is a profile of the ground emission as picked up at a fixed elevation by the CBAS telescope in the north, as we slew the telescope in azimuth. And what we basically see is just the pickup from the nearby mountain. So the observatory is in the Owens Valley Ridge Observatory. Being in a valley, we have mountains either side. And so these show very clearly as we slew the telescope. We also, one of the key features we pick up during the observing time was the Karma microwave link, which was another nearby telescope interferometer working at 30 gigahertz at alpha. Now, we produce these templates on a daily basis, and you can see on the left is a waterfall plot showing how these change over time. And now there are day-to-day variations. These are usually quite small. We were quite fortunate to find that actually the ground templates do not vary strongly, not even season to season. So winter to summer differences are usually quite small, although they are weather dependent, and they are dependent on day and night, so that you can get quite large differences during the day. Generally, we only use the nighttime data. Now, if we were to not do anything about the ground emission, we end up with maps that look something like this. So these are pretty horrible. These are very early maps of the CBAS survey. And you can see that the emission from the ground massively dominates over most of the diffuse emission away from the plane in both polarized intensity and intensity. However, the method that we've devised to remove these, remove the ground, is we produce these daily templates and subtract it from the time order data. This is actually an iterative process that involves going back several times before the ground templates fully converge. And what we have found that we can do, we can achieve about 1% improvement in terms of reduction of the ground signal in the final maps. So the initial signal is about 0.1 millik, and we 0.1 Kelvin, about 100 millik, and we can get it down to 1 millik or better in general across the whole sky. And again, these are dominating larger scales, which are usually the most uncertain. So we're doing very well to be able to reduce it to that level. On top of that, though, unfortunately, a side effect of this ground removal process is we do actually have, and this is probably one of our largest remaining large-scale systematics in the maps, are these systematics associated with the ground averaged signal. So what that means is, if we look at this top right plot, this is reprojecting the sky into azimuth and right ascension. So when we produce our ground profiles, or the profiles of the ground emission, we are basically taking slices across at fixed right ascensions across this map. So you can see on the right here, this is the ground emission. This is what this map would look like with the ground emission still included. And on the left is what it looks like when you do not include the ground emission, when it has been subtracted. But at every right ascension, there is still going to be true sky signal. There's still going to be emission there. And that essentially gets imprinted into the map. So what we've done here, this is a residual map where we've taken our best estimate of the CBAS sky signal and subtracted it using ancillary data sets. And we can see that when we average that as a function of declination on the right here, we have this residual structure, which is this ground imprinted signal. And this is mostly, as I said, it's a function of declination that we can model, and then we attempt to subtract that as well. What I'll show later that we can't remove everything, but we can suppress this significantly. The other main the other main systematic within the system was a 1.2 hertz microphonics signal caused by an oscillation in the cryogenics, in the cold head of the cryogenics. So on the right here, we can see that there is this oscillating signal. This is the raw time of the data coming out of CBAS in the top panel. And if you take a Fourier transform of this and look at the power spectrum on the left, you can see that you get these spikes, one at 1.2 hertz, 2.4, 3.6, and all the other higher harmonics of 1.2. And what we do is we essentially do this iterative process where we fit for these spikes in the Fourier plane and then subtract them until we reach a point where our uncertainty in the fit is equal to the noise level of the power spectrum or that Fourier mode. And in doing that, we are able to produce this red line, which is essentially a template of the 1.2 hertz signal, which we can subtract then from the data, and we end up with close to Gaussian noise, other than low-level correlated with ref noise and the sky signal, but we can model out the 1.2 hertz. Now, in terms of the map, if we don't do anything about it, we would end up with a signal that looks like this. This is from a simulation where most of that excess power is translated to 1 degree scales. In terms of the power spectrum, you would get this black dashed line where you have a sort of a large excess of power at about 180 degrees, at 100 L of 180, that slowly ramps off at higher L nodes. However, through our procedure for removing this, we can then use jackknife analyses to look for residual 1.2 hertz in the map at the end of the survey, after our attempt to remove it using that method described earlier. We can see that there is no evidence of this 1.2 hertz signal around the L of 180 L node. So we estimate again that this is probably removed. This is removed to about a level of 1 to 2%. One of the other important aspects, of course, one of the key aspects of CBAS is the calibration. We want to make sure that the calibration of the map is as good as it can possibly be. Now, of course, some of that came from those early designs of the optics, but there's also our approach to the calibration procedure overall. So calibration, relative calibration between the inputs is done via a noise diode that's injected early on in the receiver system, in the front end of the receiver system. We then calibrate to the absolute calibration scale using tau A. And then finally, we use models of the beam, which you can see on the right here. So the purple line is our model generated using GRASP, compared with point sources in the map, such as Virgo A, M42, and Orion, Tau A, the 3 brightest point sources and cleanest point sources within the map. You can see that we are reconstructing the first and second side lobe from the beam model to very high accuracy. We use this beam model combined with these real measurements in the map to deconvolve the beam, and it is a 99% of the beam power is actually contained within these first few side lobes. So we are able to remove any scale dependence essentially of the calibration from these maps. So what you see is what you get essentially, and you can compare this very easily then to WMAP and Planck maps at higher frequencies. So this overall calibration, we are aiming for about 1% in terms of the absolute calibration, although that exact number hasn't been finally calculated, but will be available when we release the final survey. We also do detailed calibration of the polarization signal, where we can reduce the QU mixing to less than 10%, and the out to QU leakage to 1%. And we do this through measurements of tau A. And what you're seeing here on the right is how we diagnose the Mueller matrices for the QU signal by measuring tau A at a range of parallactic angles. We measure the QU here in the horizon frame of the telescope. And in the horizon frame of the telescope, the QU of tau A should lie in the circle if it's perfectly calibrated. When we measure it from the system raw, we get these red dots. And then after calibration to the known calibration angle of tau A, we get these black dots. So that is how we do the calibration of the polarization. Now, I'm running low on time, so just to quickly summarize some of the other things that we have. RFI isn't a major issue to CBAS, just because we have, earlier on in the experiment, we included notch filters that cut out about half a gigahertz of the band around the center, which removes emission from these satellites and local RFI sources that can be seen in the sky on this top panel, and then a comparison what it looks like after we remove that chunk of the band in the bottom panel. We also do source subtraction. This will be one of the data products that we release with CBAS, where we are using our own internal catalog to remove bright sources brighter than the Jansky, and faint sources we use existing 5 gigahertz catalogs from GB6 and PMN. We do this mostly because the intensity map is actually confusion source limited. So this actually gives us slightly more sensitivity to the larger scale structures in the map by removing these point sources. And then finally, just to talk about some of the Jackknife tests. So this is how we assess the data quality. So what we're doing here in the top panel, we are seeing all the observations that have been taken with a observation ID that has an odd number. And in the second row, we are seeing all the observations that have indexes that are even. And in the bottom panel, we are seeing the differences between those two. In intensity, you can, if you squint at these maps, you can see some structures, large scale structures. But I would like to point out that the scales here are different. So, and the actual magnitude of these structures is very small compared to the actual total intensity signal. And that becomes more clear if we look at the power spectrum of those jackknives. So this is the Q and U power spectrum. The purple line here is the total signal of the map. The yellow line is the expected noise, should it be all white noise. And the black line is the measured power spectrum of the residuals in the last, on the last slide. And what we find is essentially that at large scales, we only start seeing any emission, systematic emission on large scales coming in at L's of about 20, which is about, it's scales of 10 degrees or more, essentially, is where things start showing up. But even then, they are 1% of the actual total emission away from the galactic plane. So it's 1% of the emission away from the galactic plane. Then you can also reproject these power spectrum into ALM space. So these are corner plots in ALM space. So the M modes are shown on the y-axis and the L modes are shown on the x-axis. This first panel shows the full ALM range of CBAS, where we can see the vast majority of this is consistent with white noise. We've done tests against white noise realization to verify this. And then on the right, we zoom in on this corner between up to L and M of 100 or so, or 80. And what you can see is we do start seeing some residual emission at this point. And if you remember from earlier, I was saying there is a residual sky, an average sky signal that gets imprinted into the maps. That is what is the cause of this excess here when n equals 0, so that it's a function of declination, which can be modeled out and reduced, but that is probably our most contaminated mode. But the vast majority of the ALM space, as you can see in this sort of, if you look in this central triangle, is actually very clean. And if you compare it to this plot on the right, which just shows what white noise would look like in this instance, you can see that it's very, very clean. And that's it. So these are the CBAS maps again. We just, I'm sure people are wondering when these maps are coming out. We intend to release the Northern Survey papers within the next year, and shortly after we'll be releasing the maps as well. The Southern Survey is expected to be completed in the next 2 to 3 years, just as we wait essentially for the telescope to come back online after a delay due to COVID. And the data products that we're going to release are, of course, the maps, the deconvolved map, we're going to have the beams, we're going to have the source subtracted maps. We're going to try and give as much information to the community as possible. And one very quick last thing, we are releasing papers with the intensity data. So if you haven't read it, I just released a paper using the intensity data recently. It's just been accepted by monthly notices. And we were basically looking at the robustness of the anomalous microwave emission and the spectral indices of synchrotron emission across the sky using CBAS. So yeah, I think I'll stop there and I'll allow any questions.